Today I'm going to present 3 examples of products from enolate condensation reactions. The 3 products are shown on the screen, and before we go on, I'd like you to pause for a moment and see if you can identify alpha and beta, that is, the bond that will be formed in this reaction. Did you choose the alpha beta that is shown for each of these? Here's the only carbonyl, here's alpha, and here's beta to that only carbonyl. Here we have a dicarbonyl. The alpha would be the position in between that would be deprotonated most readily, and beta would be the position it was attached to. Or wait, we could have another beta, also alpha to this carbonyl. So in fact, there are 2 possible ways we can imagine disconnecting the middle one. And finally, we have a beta dicarbonyl, and we also have a 1, 2, 3, 4, 5 dicarbonyl. Whenever you see 1, 2, 3, 4, 5 dicarbonyl, you think Michael addition. And the alpha-beta bond must have been formed between an enolate ion alpha and an alpha-beta unsaturated. So we can imagine that this is the bond that was made during the reaction, that this could have been the bond that was made during the reaction, and that this could have been the bond that was made during the reaction. We also could have had a second bond made for the middle product. So for each of these reactions, we know that we made an alpha-beta bond and that the alpha was the nucleophile in the reaction. So if we imagine taking it apart, we must have had a negative charge on the alpha position. That means the beta position must have been the electrophile. And for our reactions, such as an aldol, which is the top one, the electrophile was the delta positive that is on the carbonyl carbon. Now we recognize this as an aldol because it is a carbonyl and an alpha-beta unsaturated group. That is the product of an aldol. Aldols are condensation of 2 ketones, 2 aldehydes, or a ketone plus an aldehyde. In this case, because this alpha-beta bond was made, this must have been the enolate, the nucleophile, and this must have been the electrophile. If we make that into actual species, the receiving end must have been an aldehyde. The donating end must have been the alpha position on a ketone. So overall, if I were to do this reaction forward, I would need to take a 1, 2, 3, 4, 5 oxohexanal, 6-carbon aldehyde, and treat it with an appropriate base. An appropriate base for a plain old aldol condensation is sodium hydroxide or potassium hydroxide, or sodium or potassium alkoxide, where you have a negative charge on oxygen plus minus, and the negative charge on oxygen is localized. That is a strong enough base to remove an alpha hydrogen on a ketone or aldehyde. Another question I got a lot of on the papers today was, how do you do intramolecular cyclizations? And here is an example. If you see a substrate such as the one on the right, and it has 2 carbonyls in it, 2 ketones or 2 aldehydes, or 1 ketone and 1 aldehyde, you look to see if there's any alpha position. There's an alpha position right here, here, and here on the starting aldo ketone. Any of those alpha positions can be pulled off, have a hydrogen pulled off, and make an enolate ion using a base such as sodium hydroxide or sodium alkoxide. Only this one, when it's an enolate ion, can then add to the carbonyl to make a net 6-membered ring. Rings are only particularly stable when they're 5 or 6-membered rings, and alpha carbon has to be 5 or 6 carbons away from the receiving carbonyl carbon. In this case, it's 6. Our second example, if you look carefully at the product, it's a beta keto ester. Beta keto esters are normally formed from Claisen condensations, which are condensations of 2 ester molecules. You notice that the alpha was easy to find because it was next to the 2 carbonyls, and relative to the ester, we find the beta, not relative to the ketone. The reason for that is in Claisen condensation, one end of the ester loses its ester ethoxy group in the mechanism. Again, you see a beta keto ester, the alpha is between the 2 carbonyls, the beta is on the ketone carbon, and the bond that was made was between that alpha and that beta. So if we imagine that bond being made, we had pieces that look something like this. Once again, the alpha carbon is the enolate ion, the nucleophile, and the beta carbon is the delta positive electrophile. And when these two join together with the nucleophile adding to the electrophile, then we end up making our new carbon-carbon bond. Of course, this is just a picture with synthons. We can't actually go to the chemical store and buy the enolate ion. What we buy instead is the neutral form, and we remove the alpha hydrogen with the appropriate base. And we can't go to the chemical store and buy any psyllium ion like this. What we do is we buy the actual ester equivalent. And to start this reaction, we need to add an appropriate base. So if we take the two esters on the right-hand side and we treat them with the sodium salt or the potassium salt of the same alkoxide, in this case sodium ethoxide, then if we have any reactions that take place between the ethoxide and the ester group, we will just exchange one O ethoxide for the other, and we won't see that happening. Then this base can also take off an alpha hydrogen, make the enolate ion. The enolate ion can add to the carbonyl with the ethyl group on it. It makes an intermediate, kicks off the ethyl group, and we make our new alpha-beta bond. The other bond here, the other alpha-beta I did not show being made, would be made through an acetoacetic ester type of synthesis. The final example is one of our Michael reactions. And again, remember we picked alpha because it was between the two carbonyls. It was going to be the position that would make the best enolate ion. It would also be a relatively stable weak base that would add reversibly to an alpha-beta unsaturated carbonyl. So if we imagine what happened before that alpha-beta bond was made, we would have our two pieces, the enolate ion on top and the receiving end on the bottom. The receiving end of this particular one is an alpha-beta unsaturated carbonyl. You might have noticed I just got rid of a methyl because I can't have 5 bonds to carbon. Okay, so if I had this product, this alpha-beta bond could have been made by a conjugate addition between this enolate ion adding to this alpha-beta unsaturated carbonyl. And we know we did our Michael reaction. Our Michael reaction can start with an enolate that is formed from 2 ketones, a beta diketone, a beta ketoaldehyde like this one. There can be an ester on one or both ends, and as we saw today in class, there can even be things like nitrile groups, carboxylic acid equivalents on one or the other end. Likewise, our alpha-beta unsaturated system can be an ester, as it's shown, or it could be a ketone or an aldehyde or any other carboxylic acid equivalent. So in summary, if we want to take apart or imagine what came before with our alpha-beta unsaturated system, step 1 is to identify the correct alpha-beta. If you have a dicarbonyl, the alpha is going to be between those two. If you have a beta keto ester, it's likely is you formed it through an ester enolate process, and that implies that the alpha-beta bond was between alpha and the ketone carbonyl. If you have a 1,5-dicarbonyl, chances are you formed it through a Michael reaction in which your alpha between your two carbonyls was attached to your beta that was also the beta of the alpha-beta unsaturated system to which you did a conjugate addition. Once again, of course, you do need a base to make that reaction happen, and the base that's normally used in the reaction is the metal ion plus with the O-alkyl group, O-ethoxy in this case, that matches any esters you have in your substrate.